this video, we will learn about how electromagnets work. You can make an electromagnet out of simple materials around your home or from the hardware store. We've used a 4 by 3/8 inch lag bolt, 22 gauge insulated wire, and an alkaline D-cell battery. In the early 19th century, physicist Hans Christian Ørsted noticed that a compass changes direction when it is brought close to a live wire, thus showing that moving electric charges produce magnetic fields. He observed that if the current is run in the opposite direction, then the direction of the magnetic field lines also reverses. Note that the compass needle will align with the direction of the magnetic field lines in that region of space. We can determine the direction of the magnetic field lines using the right-hand grip rule. The thumb points in the direction of conventional current, that is, the flow of positive charges, and the fingers indicate the direction of the magnetic field lines, which encircle the wire in the plane perpendicular to the wire. Another physicist, André-Marie Ampère, furthered Ørsted's work by studying the magnetic field produced by running current through a long coil of wire called a solenoid. He noticed that a strong, uniform magnetic field was produced inside the solenoid. Most electromagnets are made of solenoids, sometimes with a ferromagnetic core material such as iron, as is the case for our homemade electromagnet. Notice that we can use a modified right-hand rule to represent the direction of conventional current through the solenoid with our fingers, and the magnetic field direction inside the solenoid with our thumb. Let's test our electromagnet and see if we can replicate some of Ampere's and Ørsted's findings. We can use a compass to identify the polarity of the electromagnet. Note that the south pole of the compass will align with the north pole of the electromagnet, and the north pole of the compass will align with the south pole of the electromagnet. By flipping the battery, we reverse the direction of the current through the solenoid, and the direction of the magnetic field inside the solenoid is reversed, which causes the polarity of the electromagnet to flip. We can also vary the number of turns of wire in a solenoid and observe the effect on the magnetic field produced. The first electromagnet has approximately 50 turns over the length of the bolt. Notice how much load it can lift. Note that the greater the magnetic field an electromagnet produces, the greater the magnetic force that it can exert. The second electromagnet has approximately double the number of turns per unit length as the first. Observe that increasing the number of turns per unit length increased the strength of the magnetic field produced. The main benefit of an electromagnet is that, unlike a permanent magnet, its magnetic field can be controlled by adjusting the current through the solenoid. To demonstrate, we will connect two D-cell batteries in parallel to increase the current flowing through the solenoid. Notice that the magnetic field strength increases in response. We can summarize our findings in a mathematical approximation for the magnetic field inside a solenoid, sometimes referred to as Ampere's law for solenoids. The constant of proportionality, mu, is a value that depends on the core material and is called the permeability. If no core material is used, the constant is equal to mu naught, the permeability of free space. Please check out the linked PhET simulation to further investigate these relationships quantitatively, and also to see how changing magnetic flux can produce electric current.